Look at these classical pillars. In the late 1960s, the University of Ceylon's engineering faculty served as the premier proving ground for the region's sharpest minds. 293 students arrived on this campus in 1967 and 1968. They came to learn the exact mathematical and physical laws required to build the modern world. Over the next 50 years, these engineers fanned out across the globe, applying their rigorous training to international infrastructure and technological grids. They survived punishing exams and built an intense camaraderie, one forged through late-night study sessions and weekend hikes scaling the local Hantana Mountains together. This university training ingrained a lifelong systems thinking mindset, a shared language of problem-solving that permanently bonded the group together. Fast forward to today. Those same students are now navigating their late 70s. We now have a longitudinal study tracking the lifespans of this exact cohort, the EFB67&68 group. Over the following 5 decades, this group spread across the globe to design, build, and maintain the physical infrastructure of the modern world. Now, as the majority of these engineers navigate their late 70s, they are applying their systematic problem-solving skills to a completely different type of system, their own biological timelines. This waterfall chart tracks their initial Veda audit. Starting from the left with the baseline cohort of 293, we subtract early dropouts and 62 documented departures to arrive at the active study group, 231 surviving members. The cohort treats this actuarial tracking as an active engineering project, applying technical rigor to their own biological legacy. The data required adjusting for geography. Following periods of geopolitical instability in 1983, a massive migration scattered the cohort, creating distinct population clusters in Sri Lanka, the UK, and Australia. Over the last 4 decades, researchers recorded 62 specific departures. But there is a mathematical problem with the 231 members still alive today. When biostatisticians plug the data of the survivors living in Sri Lanka into standard prediction formulas, the models systematically underestimate how long these individuals will actually live. In standard epidemiology, wealth and high professional status almost universally correlate with a longer lifespan. Higher income careers typically buy more years of health. This chart maps the average age of departed members in this specific cohort. The data shows an anomaly. The engineers who emigrated to the UK and Europe lived to an average age of 72. Those in Canada and the US reached 68. But the engineers who remained in Sri Lanka, the elite of the local professional class, died at an average age of 60.6. This discrepancy is known as the status syndrome paradox, or a reverse socioeconomic gradient. For this cohort, the success that led to urban wealth in South Asia unexpectedly worked against their biology. Climbing to the top of the socioeconomic ladder in a developing urban economy exposed them to environmental stressors and systemic healthcare gaps. A high-hazard environment acts as a grim filter. In Sri Lanka, 1980 civil conflict and lacking cardiovascular care acted as these hazards, accounting for a massive 32.3% of the cohort's premature deaths. This leaves us with the 133 cohort members still living in Sri Lanka today. They survived that intense period of early attrition. That means they are a highly selected, biologically robust elite. Having cleared the heavy harvesting phase of middle-age mortality, their current intrinsic physiological reserve is far stronger than a standard Western population of the exact same chronological age. Because the raw historical data from the 1980s and 90s is so heavily skewed by those premature deaths, relying on it to predict the future mathematically guarantees an underestimation of the remaining cohort's lifespan. To get an accurate picture of how long these 231 living members will actually survive, biostatisticians have to adjust the formulas and look forward. This panel illustrates a concept called right censoring. We know the exact departure dates for those who passed away, but for the survivors, their story is still being written. The math uses this incomplete, right-censored data to calculate future probability, without assuming living members will live forever. These 231 survivors, the data reaches a threshold called right censoring. We have a documented history for every member up to 2026, but because their lives are ongoing, survival models must calculate future probabilities using the incomplete, censored information we have today. This line graph maps out the 62 departures we've seen. Notice the long, shallow tail stretching through their younger years. During this period, departure risk was dominated by what actuaries call the Maycam constant, random environmental hazards and accidents, rather than internal biological aging. A person's baseline survival through midlife is heavily dictated by their zip code, random environmental risks, and early medical access. But as the cohort steps past the age of 75, the variables dominating the equation are changing. Past the age of 75, the cohort crosses a biological inflection point. The risk of death is no longer a flat, predictable line driven by random accidents. It begins to accelerate. This is the Gompertz exponential timer. It is the biological law dictating that once a human reaches late adulthood, the internal cellular decay of the body compounds. From this point forward, the risk of mortality doubles roughly every 8 years. This graph models future departures using 4 formulas. The blue cubic polynomial line fits historical data perfectly, but without biological rules, it swings in wild, unrealistic directions. Instead, look at the red Gompertz trajectory. It's the gold standard because it strictly obeys human biology. The math must also account for clinical medical breakthroughs expected to arrive over the next 10 to 25 years. This timeline illustrates the expected integration of these advances. Within 5 years, AI-driven diagnostics will drastically reduce acute mortality risks. Following that, treatments like systemic senolytics will become clinically available to clear out inflammatory aging cells and actively delay physiological decline. However, geography dictates who gets these treatments first. While cloud-based AI diagnostics can deploy anywhere, advanced physical therapies face severe regulatory and financial lags of 5 to 10 years in Sri Lanka. Even when those drugs arrive, they will fight continuous environmental re-injury. The systemic inflammation caused by chronic urban air pollution, shown here in Colombo, will actively neutralize the benefits of these therapeutics. Science will add years to their health span, but surviving members living in Sri Lanka cannot simply wait for delayed Western therapeutics to arrive. Because these advanced therapeutics will be delayed, physical maintenance becomes the primary tool for survival. The cohort carries a specific genetic vulnerability known as the South Asian cardiometabolic phenotype, which presents a higher risk of early microvascular disease. To combat this, members must adhere to stricter clinical guidelines than standard Western populations. For instance, they need to maintain a body mass index below 23 to manage visceral fat. They also need to integrate continuous resistance and balance training into their routines to prevent age-related muscle loss, known as sarcopenia, and to avoid catastrophic falls. And to protect against the sharp post-retirement memory decline often seen in elite professionals, they must maintain aggressive social connectivity and regular cognitive stimulation. Securing an extended lifespan relies heavily on treating the human body with the exact same rigorous preventative maintenance schedules they spent their careers applying to engineering projects. Living to 100 carries an overlooked vulnerability. An extended lifespan creates a high probability that an individual will outlive their own legal and financial protections. Extending the human lifespan changes the math of retirement, creating a logistical gap that standard financial models were never designed to cover. To address this, members must conduct a 100-year financial stress test. Standard retirement savings often deplete by age 85, leaving a vulnerable, unfunded care gap stretching to 100. Protecting those extra years requires critical legal safeguards, a task made exponentially more difficult when a cohort is scattered across international borders. This global legacy planning grid illustrates the immense complexity of cross-border administration. Essential documents like enduring powers of attorney and wills vary wildly depending on whether you reside in the US, the UK, or Sri Lanka. In Sri Lanka, this manifests as the enduring power gap. A standard general power of attorney is legally terminated the exact moment a person suffers cognitive decline. Bridging this gap requires urgent legal countermeasures. Members must secure jurisdiction-specific last wills, establish protective family trusts, and outline exact advanced medical directives. Financially, existing assets should be specifically structured to pre-fund private, professional in-home care, moving away from an exclusive reliance on family members for daily physical support. The EFB67 and 68 cohort successfully engineered a nation's infrastructure. Armed with this biological data, their final task is to proactively engineer their own enduring legacy, while they still possess the full capacity to do so.